Alright, in this next example of finding the expressions for the beam deflection, we got a couple of things that are going on here. And that is, with this cantilever beam fixed end to the right, we have an applied load of P equal 20 kips downwards out here at the left, and we got an applied moment of 100 kip foot being applied again right here at the end of this 15-foot long cantilever beam. Right? We're trying to find the transverse deflection and then maybe the value and location of the maximum displacement, whatever that's supposed to mean. Right? So we'll worry about some of these subtle details as we go along, but one of the big keys here is that, hey, what we're working with is our governing model that says that the second derivative of the curvature is equal to the intensity of the distributed load. Right? Okay, so that's the basic model. Fourth order differential equation. It's a boundary value problem. And so let's identify the coordinate system we're going to use, and let's then also set up these boundary conditions. Right? So we'll go to the far left. It's like that pen doesn't want to work real well there. We'll go to the far left to set up our coordinate system, and we'll use positive upwards for our displacement. Right? So basically a Cartesian coordinate system. Right? So there's our coordinate system that we're using. Now the boundary conditions are going to be that over here at the far right we're going to have no rotation and we're going to have no transverse displacement. That's at x equal to L. That both of those are going to be true. Right? Now, yes, by simple equilibrium I could find the moment and the shear here, but that's not a boundary condition. Right? That's the result of applying the rules of equilibrium. Right here, now over here at the other edge, I don't know what the transverse displacement is. I don't know what the rotations are, but I do know what the imposed loads are. And so there we know that with our positive sign convention, smiley face is this direction, so our moment would be equal to a plus 100 kip foot, but our shear would be opposite of, in terms of positive, and so our shear is equal to a minus 20 kips right there at x equal to 0. Well, technically just a little bit to the right of the applied load. Right? We have no distributed load, so this is easy here. The distributed load value, that function Q, is equal to 0. Right? And certainly some of what we're going to do here is going to be a lot easier as a result. Right? We've got, okay, Q of x is equal to 0, and so the shear is equal to the integral of Q of x. That's the integral of 0, which means that's going to be a constant. And note, we do have a boundary condition associated with the shear, so let's evaluate this. V at x equal to 0 is equal to C1, and that's supposed to be equal to minus 20. Therefore, we just found our first boundary condition. Right? That seemed a little bit too easy, didn't it? But sometimes it does work out that way. Right? Now we have the shear function, which is a very easy one. Right? Right? Let's just even draw that real quick. There's our shear, and so there's 0, there's L, and our shear will be equal all the way across to minus 20 kips, of course, in that instance, and that's what that function just told us. Right, well, now let's go find our moment. Moment is the integral of shear, so the integral of minus 20 times dx, that's minus 20x plus our second constant of integration. And yeah, we have our second boundary condition here that says that at x equal to 0, our moment is minus 20 times 0 plus C2, and it's supposed to be equal to a plus 100. So therefore, evaluating that, we find out that our second constant is equal to a plus 100, or in this case actually kip feet. Right? And so finally, then that means our moment function is equal to minus 20x plus 100 cubic feet. And if we were to draw that out, then of course it's just the equation of a straight line, right? And where it starts out at plus 100, and over here at x equal to L, which is 15 feet, well, minus 20 times 15 is minus 300, so minus 300 plus 100 leaves us with a net of a negative 200. Right? And I'm not quite sure if you can see all that, but there you go. There's that. That just matches exactly with what we'd find for the reactions here. There's 20 kips there, and there's a moment of 200 that goes along. Hey, if I sum moments right at this point, I'd have then 20 times 15, that'd be going this way, that'd be 300 going in a counterclockwise fashion. I've got the 100 right here going the other way. I need this net of 200 to make that be put into equilibrium. Okay, so that's the moment function right there. Now we go find curvature, and so kappa equals m over ei equals 1 over ei. That's a constant, and that'd be minus 20x plus 100 would be that function right there. Slope is the integral of curvature. So the integral of 1 over ei minus 20x plus 100. Notice other times I've shown you how to pull the ei out of here and do ei theta. That's what we oftentimes do out of convenience. This time I'm just showing it to you as is. 1 over ei constant comes out of the integral. We'll get minus 20x, which would be minus 10x squared, right? 20x squared over 2, plus 100x, plus our third constant. And we know that at x equal to L, theta equals 0. So theta at L equals 1 over ei minus 10 times 15 feet squared plus 100 times 15 feet plus C3 is equal to 0. So the EI goes away, and we get, that's 225, so that's minus 2250 plus 1500 plus C3 equals 0, and so C3 is, that's 750, goes the other side. Whew, 750. What the heck are its units? Alright, well, go back to here. The 100 had kip feet units on it. I integrated it. It's still kip foot there times, then x would be feet. So that was kip feet times feet, and the EI had its own units. But as I work through this, see the C3 right now doesn't have the EI in it. So this is kip foot squared on its units. Alright, so let's see, we've got one more to do. Displacement is the integral of the slope. So that's the integral of, well, here's our 1 over EI minus 10x squared plus 100x plus C3. I'm going to leave it like that. I know it's a number, I just want to leave it like that right now. Sometimes this is easier just to work it all the way out like this. 1 over EI, that becomes minus 5x cubed plus, then this will be x squared, 100 divided by 2 would be 50x squared plus C3x plus C4. And, wow, okay. So now the displacement boundary condition is that V at x equal to 15 feet is going to be 0. 1 over EI minus 5 times 15 cubed plus 50 times 15 squared, plus, and C3 was 750 times 15 plus C4, and that all has to be equal to 0. Right, well, let's see what that's going to work out to be. 5 times 15 cubed plus, well, that's supposed to be a minus. Let's do this backwards. 750 times 15 plus 50 times 15 squared minus the 5 times the 15 cubed. And that's a plus 5625 kip foot cubed. How did I know that? Well, because the 750 was kip feet squared times another foot, right? And that was plus C4 equals 0, so therefore C4 equals minus 5625 kip foot cubed. Right, so that's going to give us an expression for our displacement. V of x is going to be equal to 1 over EI, and then minus 5x cubed plus 50x squared plus 750x minus 5625, and we ought to note that that numerator has units of kip foot cubed, so that when we evaluate and put the EI in there, whatever values those are, we work backwards to an appropriate set of units for our displacement. Right, so that's the moment expression. Now, what they've also asked us to do is to find the maximum displacements. Right, well, Vmax, of course, is going to be located where theta, the slope, is equal to 0. Now, the thing is here that we know that the slope is 0 at the fixed end. That's not what we're really going after here, right? So let's take a look at what happens to this system in sort of multiple parts. Right? So let me slide this up a little bit for you. The deflection that happens due to just the point load out at the end should be reasonably predictable, that it would look something like so, curving down, bam, like that. Right? Well, we're going to add to this the deflections that happen from the end moment. Well, that's just a smiley face, and that's a perfect or uniform moment along the length of the beam, so that would actually be the same curvature. That would actually be an arc of a circle, it would turn out. And it would look something like that. The combination of these two is going to be kind of interesting here. Note, it's a superposition, of course, of these two functions, and that's what we've got right up here. Some of it being caused by that load, some of it being caused by the moment, right? It's going to, but notice in both of these cases, the tip actually has a maximum displacement. Now, look at what we got for a moment diagram. We have negative curvature over here, and we have positive curvature out at the end, right? And when you look at the 100 to 200 ratio here, then this would be go over 2/3 of L, and that would go over 1/3 of L, so that's 5 feet as compared to 10 feet that we have the curvatures. Now that's not a point of 0 displacement. That just says that I go back, I've got frowny face curvature that is largest over here by the support, and that goes along for 10 feet from the right hand support, because the moment is like that. Right, so that goes down like that, and then we start to swing back the other way. I don't know how far we swing back, but we start to swing back the other way with the positive curvature. We have slope continuity right here at the transition point, but it would look to me like that the point load out here had a bigger effect than what the moment did overall, right, when you look at the combination. And we see that just from the moment diagram as a whole. So I don't think we'll find this condition here. I think we'll find Vmax at the end, right at that location. How do we know? Well, what I would do is I'd find out, I'd evaluate the slope for where it's equal to 0, and then, and that's of course going to be right here, and if it doesn't show up anywhere at the domain, within the domain elsewise, well then I know that, then I got to go check this Vmax out here, and that's where the maximum displacement is going to be. Whew, it's a lot of effort, isn't it? You better believe it is. That's why people love beam deflections so much.